Welcome everybody to the next video in our series on probability and statistics. Today we'll be talking about the gamma family of distributions. So what is the gamma function? So that's a good place to begin. Well, the honest and simple answer is that the gamma function is the function which generalizes the factorial function. So we'll recall that the factorial function was really defined on the positive integers. And if we had n being a positive integer, then n factorial was calculated using n times n minus 1 times n minus 2 all the way down to 2 times 1. And so what we had was that 1 factorial was just 1, 2 factorial was 2, 3 factorial was 6, 4 factorial 24, 5 factorial 120, and so on and so on. But then the real question was, what if we somehow wanted to calculate 5.5 factorial? Since that's not really a positive integer, then our definition really doesn't make sense. So somehow we need to extend our notion of what we mean by factorials. And so as a reference, I provide this particular article. It's a bit old, but it's still an incredibly good article. It's called Leonhard Euler's Integral, a Historical Profile of the Gamma Function. And so that was written by Philip Davis back in 1959. It appeared in the American Mathematical Monthly. So if you want to look that up, I provide you the reference. I encourage you to read it if you want to know a little bit more about the history of the gamma function, more than what I'm going to provide here. So Davis kind of goes into a little bit more of the detail, a little bit more of the history of how Euler actually came up with the gamma function. And he starts out with the very question with which we started, basically, what would be something like 5.5 factorial? So I encourage you to look it up. It's out there on the internet. It's an excellent reference. So now introducing the gamma function. So the definition of the gamma function, if we let x be any positive real number, then we'll define gamma of x to be the integral from 0 up to infinity of t to the x minus 1 e to the negative t dt. Now, since that is an integral, and it's an infinite integral, one thing that we really need to be worried about is convergence. So does that thing actually give us finite answers? And so let's start looking at the convergence of the gamma function for just the positive integers. So if we let x be a positive integer, and in particular, if we let x equal 1, well, if we plug 1 in for x, then we get this integral from 0 up to b of e to the negative t dt. We then take the limit as b goes off to infinity, and sure enough, we get a finite value. We get a value of 1 in that case. And so what that tells us is that the gamma of 1 is 1. And so now we're going to actually perform this part of our discussion using the principle of math induction. And so we need an induction hypothesis. And so we'll assume that convergence holds up to some positive integer n. So let's perform an integration by parts on our gamma function. And so if we let u be t to the n plus 1 and dv dt be e to the negative t dt, then we perform an integration by parts and we get an expression that looks like this. Now for this first part, the e to the negative t to the n plus 1 e to the negative t from 0 to b, if we take the limit as b goes up to infinity, then repeated application of L'Hopital's rule from calculus will end up showing us that that limit is going to be 0. And then by our induction hypothesis, the integral on the right-hand side, as b goes off to infinity, well, that is just our gamma function evaluated at a previous value of n. And so what happens, gamma of n plus 1, we're able to write that as n plus 1 times gamma of n. And by our induction hypothesis, that's finite, so gamma of n plus 1 is finite. So by the principle of mathematical induction, we know that the gamma function is going to converge for all positive integers. So now if we let x be any real number, in particular any real number greater than 1, but we let it be arbitrary, now we'll use the floor function, so the greatest integer function. So we look at the greatest integer function that's less than x, we add 1 to that, and then we use this property from real analysis that if we have two functions, f and g, and f is greater than or equal to 0, and g is going to be greater than or equal to f on an interval a, b, then the integrals also respect that ordering. So the integral from a to b of f is going to be less than or equal to the integral from a to b of g. And so we can write our integral from 0 to b of t to the x minus 1 e to the negative t as the integral from 0 to 1 plus the integral from 1 up to b. If we can replace this ordering for t to the x minus 1 whenever t is greater than or equal to 1 by this value. And because our exponent happens to be an integer in this case, then as we take the limit as b goes to infinity, we get the gamma function evaluated at an integer, and so we get convergence. And so what that means is that our original integral for x also converges. Now, kind of the last thing that we need to check is what happens if we pick an x value between 0 and 1. Well, in this case, now we need to check both for convergence at both 0 and infinity. So again, using an integration by parts, we've got u as e to the negative t and dv as t to the x minus 1 dt. So we have to check at convergence at 0 because since x was between 0 and 1, x minus 1 is going to be negative. And so we've got a 0, potential 0 in the denominator there. And so we look at du and we look at v. Doing our integration by parts from a up to b, we get an expression that looks like this. Now that we can see in the case where a goes to 0 and b goes to infinity that our integral 1 over x of the integral from a to b of t to the x e to the negative t dt, that will be our gamma function evaluated at x plus 1 times 1 over x. And so because of that, we know our integral is going to converge. And likewise, for the expression evaluated at a and b, we can apply L'Hopital's rule. And so again, we get that expression is going to end up being 0. And so what this gives us is kind of a sketch of the proof that the gamma function is going to be convergent for any x on the interval from 0 up to infinity. So the gamma function is actually pretty useful in that not only can we define the real version, which is what we just did, we can also define a complex version of the gamma function. So in terms of complex numbers, the gamma function is actually defined as a meromorphic function. So what that means is it looks something like a rational function with complex numbers. So it's a meromorphic function on the complex numbers. It has simple poles at the negative integers and 0, and it's formally calculated as gamma of z is going to be an infinite product. So an infinite product from n going from 1 up to infinity of 1 plus z over n to the negative 1 power times e to the z over n, and that's going to be normalized by e to the gamma z over z, and gamma is going to be a constant chosen so that gamma of 1 is 1. Now, complex numbers are a little bit out of what we'll be dealing with in probability and statistics, at least for right now, so I'll leave that to you to, maybe look up a little bit later. Now, what we've got down here is the real part, so the real gamma function, evaluated numerically, and we've got a plot of something like that, and so that we see that we do have kind of these poles at -1, -2, -3, -4, as we would have here, and this is actually a rendering of what it would look like if what the gamma function would look like in the complex plane. Again, we see these simple poles, -1, -2, -3, -4, and so on and so on. So now here is what we really come to when we were talking about solving that very first problem, that we said that the gamma function was an extension of the factorial function. And so we really see that in this particular theorem. So that the gamma function satisfies the following properties. That on 0 to infinity, we have this functional equation, and this we kind of got by integration by parts. That gamma of x plus 1 is equal to x times gamma of x. Gamma of n plus 1 is equal to n factorial, for n being 1, 2, 3, and 4, and so on, so n being a positive integer. The log of gamma is going to be a convex function on 0 to infinity. And finally, here's this kind of last part that's important. If we have a function that satisfies any of the above properties, so if the functional equation holds, it is equal to the factorial function on the positive integers, it's the log of gamma is going to be convex, then that function is going to be the gamma function. And so those three properties actually uniquely define what the gamma function is. So that's why we can really say that the gamma function is the generalization of the factorial function. So now a function that's kind of closely related to the gamma function is called the beta function. Now the beta function, if you go back and read the article by Davis, that this is probably the function that that Euler actually started with. And so we have the beta function. It's actually a function of two variables, x and y. So if x and y are positive real numbers, then beta of x and y is defined to be the integral from 0 to 1 of t to the x minus 1 times the quantity 1 minus t to the y minus 1 dt. And as it turns out, that can be evaluated as the quotient of the gamma functions. And so beta of x and y is equal to gamma of x times gamma of y over gamma of x plus y. So, of course, we can turn this particular function into a family of distributions, really just by taking the PDF to be gamma of alpha plus beta over gamma of alpha times gamma of beta times x to the alpha minus 1 times 1 minus x to the beta minus 1. So we really just let our variable t that we had in the definition of the beta function actually be our random variable x, and we'll have that be a function on the interval from 0 to 1. Now, if you look at that maybe not too closely, but if you're staring at it, then that may vaguely remind you of the binomial distribution. And so I'd encourage you to go back, look, and remember how the binomial distribution was defined and what that thing actually looked like, and see if you can somehow see in the beta function the binomial distribution. And when you kind of see it, then exactly how do you see it? And I will leave that for you to explore a little bit on your own. And so now we're actually ready to define the gamma family of distributions. And so a continuous random variable x is said to have a gamma type probability distribution. We denote that by saying that x is distributed. So the x tilde gamma of alpha and beta, where alpha and beta are positive real numbers, if and only if the density function for x can be written as 1 over beta to the alpha times gamma of alpha times x to the alpha minus 1 e to the negative x over beta. And that will be defined for all x greater than 0. And so, of course, once we define what a probability distribution is, then we need to know what's the moment generating function. And so we have this theorem that says that if x has a gamma distribution with parameters alpha and beta, then the moment generating function is given by 1 minus beta of t to the negative alpha power. All right, so let's see why that might be true. Well, going back to the definition of our moment generating function, it's just the expected value of e to the tx. So we plug e to the tx as a multiplier for our PDF from 0 up to infinity. And what happens, we can put the exponentials together. So we've got the integral from 0 up to infinity of x to the alpha minus 1 times e to the x times 1 over beta minus t dx. Okay, so if we kind of rewrite that a little bit, then we can kind of put that 1 over beta minus t as a parameter under the x. So now that looks like a member of our gamma family of distributions, with this kind of new beta parameter of being 1 over beta minus t to the negative 1 power. And so what we can do, if we want to evaluate that, we can do a u substitution, or in this case a y substitution. So if we let y equal x over 1 over beta minus t to the negative 1 power, then here's the value we get for our dy. So making that substitution, we've got our e to the negative y power. So inside our x becomes 1 over beta minus t to the negative 1 times y. So that goes into the alpha minus 1 power. And we've got this extra factor of 1 over beta minus t to the negative 1 to the outside. That was just a constant as part of our dy. And so if we move our 1 over beta minus t to the negative 1, we distribute that power, move that as a constant to the outside, then our integral now actually looks like a gamma function on its own. And sure enough, that is the gamma of alpha. And so what happens, our gamma of alphas cancel out, and we get a 1 over beta times 1 over beta minus t to the negative alpha power. Well, if I factor out a 1 over beta from that expression, then I get a 1 over beta to the alpha times a 1 over beta to the minus alpha. And inside I have a 1 minus beta t to the minus alpha. Well, my betas cancel each other out, and I sure enough end up with my moment generating function of quantity 1 minus beta t to the negative alpha power. And so once we've got the moment generating function, of course we can do the expected values. And so if x has a gamma distribution with parameters alpha and beta, then the expected value of x, so the mean, is just going to be alpha times beta. The variance of x is going to be alpha times beta squared. So how do we get that? Of course, we take the first derivative of the moment generating function, which gives us this expression here. We plug in 0 for t, and sure enough, we get that the mean is just going to be alpha times beta. For the second moment, we take the second derivative. So take the second derivative, plug in 0, and we get a value for the second moment of beta squared alpha times alpha plus 1. So then the variance, being the second moment minus the square of the first moment, is going to give us beta squared alpha times alpha minus 1 minus alpha squared beta squared, which just gives us, sure enough, alpha times beta squared. So this has kind of been the first part of the video series in the gamma family. We really have 2 more parts to go because there's a couple of other very important families that fall underneath the gamma function. Those would be the exponential function, which is also tied to the Poisson distribution. And a second really important family will be the chi-squared family of distributions, and we'll see why that's going to be true coming up pretty soon. So I hope this has been a pretty good introduction to the gamma function, talking about some of the convergence properties and how we actually define the family of gamma distributions, the moment generating function, along with the mean and the variance. So stay tuned for the second video on this particular family, and I will see you next time.